Okay, perfect. So I'll go ahead and kick things off. Really excited to introduce our next guest speaker. He is a senior engineering manager at Adobe, specifically with the Adobe Experience Platform. And we have the pleasure to, not just like partner, but also to work with him as our key champion for DeltaLake. And so without further ado, we'd like to introduce Yesh.
I have this.
You do? Oh, okay, perfect.
Cool. Hey guys, I'm Yash. Thanks, Chris. So I'm part of the Adobe Experience Platform team, specifically the Unified Profile team. We have been using or playing with DeltaLake, I think, from 2020 onwards. It's kind of been an exciting journey since going all the way from toying around with DeltaLake as a concept versus getting stuff into production like last year. A lot of things have happened since then. So this talk hopefully gives you guys something to take back home and is useful. So before I even go into the specifics of what I want to share with respect to what we've done as a team, I think we have to go a bit into what problem are we solving. So the Unified Profile team itself, if you think of it as a concept, it's kind of a global sink for all of the marketing data that basically comes in. And Adobe, one of the things with the Adobe Experience Platform is that it's like a SaaS. It's a SaaS that a lot of Fortune 100s and Fortune 500s, they use. Imagine you're Nike. Every single click or interaction or purchase, whatever you do on the website or the app or anything, it's all going to flow into the Adobe Experience Platform. And if you want to do anything useful with it, it has to flow into the Unified Profile system. So now imagine not just Nike, but every other customer that has purchased this, which is quite a lot of them. All of this data is flowing into the Unified Profile. Now, with that set as a base, we have a lot of different sources hydrating the data. This could be streaming sources, or this could be batch sources. And when I say sources, it's like whatever click you do, or it could come from an app, or it could also be, let's say, from a CRM source. Or you went to a store and you uploaded some stuff on a form, which is again coming asynchronously into the platform. Any data possibly that could be used for marketing or targeting users, first-party data. So all of that is coming in through various different formats. It could be JSON, because there are so many different companies who are invested in this whole ecosystem even before a lot of us were born. So the formats have evolved, but they've also stayed. So you have all the way from protobuf to simple JSON to Avro or anything else. But what we do from an Adobe Experience Platform point of view is all of this gets converted into a standard format called XDM, or the Experience Data Model. Experience Data Model is nothing but, it's kind of like a tenant-oriented or like a marketing spin on top of JSON schema, so that the rest of the platform knows how to use this data downstream. Now, all of the processing for this XDM within UPS happens using Spark, and we use various modes, whether it be batch or structured streaming. Now, initially, pre-DeltaLake, all of this data was going into like a NoSQL store. Now, one of the interesting things about UPS, apart from the fact that it's like a global sink that takes everything in, what do you do with that global sink, right? It's a fun problem to just have data into the system, but what do you actually do with it? It's fun to say I have 2 petabytes, 5 petabytes, 1,000 petabytes, whatever, right, in the system. But what do you do actually with it? Do you make money with it? So there are 2 specific access patterns which we have. One is the batch scan pattern. The next one is the point lookup pattern. So we support close to hundreds of thousands of RPS on each tenant. So at the same time, we are also allowing massive scans of the data that's present or ingested into the system. So now these are 2 different problems, OLTP and OLAP. And so far, there does not exist one database which can solve this in a cost-effective manner. Cost-effective manner, ***. So that said, what we have is, what we did create in the beginning, even with the NoSQL store, was we knew that we needed to put some hooks in. So we exposed something called a change feed. Every single mutation that happens on this store basically gets emitted to a Firehose topic in Kafka, and that gets piped down so that downstream systems can use it. But still, the key point is all the main use cases, whether it be the batch or the point lookups, both were operating off of this one NoSQL DB. Imagine a 5,000 core cluster coming and hitting a NoSQL DB to do Spark scans. It worked, but worked sometimes, and it also worked at a very big cost. So that's where DeltaLake comes in, and that's why I'm here talking about it going forward. Another couple of things that we should know is that it's not just data in, that is, it's not just an append-only pattern. And what do I mean by that, right? So when I'm talking about marketing data and all of that, it's actually more of a graph problem, because, and it's a slightly a larger graph problem. The reason being, every person can be linked with various identities. And when I say identity, like yesh@gmail.com is an email identity, which could be linked to an anonymous cookie ID on my browser, or it could be to an app tracking ID on my app on my phone. So all of these things has to be combined together. So what do I mean by combined together? That's the part where we call the graph generator. So apart from storing just the raw data that each of these identities or personas actually generated, we also have to link the data for each of these personas. So that's where the problem starts getting more trickier, right? It's not just, oh, I'm just listening to a Firehose and I'm just dumping data through. So what I ended up doing is tried to simplify the layout of the data, or what kind of data we are storing, in kind of a naive way. So what I would focus mainly on is like the primary ID and the related IDs. The fields 1 to 1,000, in reality, they're close to 1 to 11,000. The primary ID basically tells you which persona generated the data. Like yesh@gmail.com, purchase something. That's what that 1, 2, 3 would refer to. The related IDs would basically be what are the other identities that I am linked to, like my cookie ID or my app ID. That's what it is. And this is what I'm referring to as a graph problem, because number one, it's like who is the data keyed against, and who else is the data keyed against, which comes from the related IDs field. Now, why is this a problem, you may ask? Because identities change. Today, I might be part of a cluster. Tomorrow, we get more information that will get split. Then what happens to all the data that's already stored? We have to go and change them. So one example that I'm showing over here is how you got one more ID come into the system, which basically triggers off a cascading change in the graph and all the associated entities with it. So hopefully, this kind of gives you a lay of the land. To summarize, what we're storing is a graph, and a graph with related fields with it. So, and this is what we're trying to model to, for some of the access patterns that we have. So I spoke about the two main access patterns, one being the point lookup, where it's like a low latency, high throughput point lookup case. That's obviously not getting solved by the DeltaLake. But the case that we are primarily concerned about is the batch scans. How can we scan more efficiently with a higher throughput? So with relation to that, the main access pattern that comes into mind is the querying thing. Because like I said, what are we actually going to do with the data, right? Like probably I want to do, hey, give me everybody who probably did a trial of Adobe Illustrator in the past 7 days, but added Adobe Photoshop to their cart in the last 3 days and did not purchase it. A SQL statement for that will be very funny to write and execute. But what we did is the way that we executed the whole thing is that we have built a layer of our own custom query engine, which takes care of performing thousands, tens and thousands of queries on top of individual records. So this way, this actually allows us to scale better. Now, access pattern-wise, right, why this is important is because this is slightly more different than how we would optimize a SQL query kind of an access pattern where you have, or like an analytics use case, where you're probably looking at a small projection of fields and you're trying to retrieve them and query on them. The reason being, here, we need, because we're running on tens and thousands of queries, the projection of the columns, which are probably necessary to run these queries themselves, also run in thousands. So most of the time, you're doing close to a full table scan in these things. So how do we optimize to fetch the data and basically be able to merge the data in real time in order to execute these things? Now, with that hook set up, right, what kind of complexities do we currently face, even with our NoSQL DB or whether we go to DeltaLake in general, right? I did mention that we convert all of this into an XTM JSON format. JSON is great. It's very simple. Anybody can load it up in their browser or their VS Code, and you can inspect it. But it's not necessarily the most efficient format that is there. Due to the JSON-ness of it, we basically promote a lot of nested fields. People, if you give somebody a hammer, they will want to smash with it. So you have things like A.B.C.D.E.F.G, as in this keeps going on and on. Now, all you need to do is make one of these elements an array or a map, and things break loose. So try optimizing on top of that. It's going to become harder and harder for us as we're going through. And added to this, like I said, we are a SaaS. It's not like, oh, we do some optimizations for one client and it just works for everybody else. That's not the case. Every client comes with their own schema. One client or tenant could have a completely flat schema, making our lives really easy. The other one could have a completely messed up, well, for me it's messed up, for them probably it's great, messed up version of referencing their hierarchical entities in the JSON, which makes things very complicated. And added to this, it's not like we can say day one, you brought some schema in, that's all that you get. Schema keeps evolving constantly. Now, this is the kind of problems that we're kind of facing with, even trying to get data into the system. So there is another aspect to this, apart from the metadata itself, is that the frequency at which the data comes in and the source of the data coming in is also completely different. Like the clicks example that I was saying, the clicks, the conversions, etc., all of that could be coming from a streaming topic. But then a lot of the CRM stuff, or like say the AI model generated scores, etc., all of that could be coming from a batch source. But all of them are going to the same sink, which we have to manage. Now, in terms of scale, apart from the metadata and these sources, all of them could have tens of or hundreds of billions of rows, as we're saying, petabytes of data independently, and millions of RPS in scale. So that said, some of the things that we've basically used from Databricks, which has actually made our lives very useful, and two of them are, I guess, open source now. One is the autoscale part, which basically helps us as it makes sure that we don't have to set up individual single tenant clusters for each of them, so that we can have a bit of multi-tenancy in a lot of our jobs. The auto-optimize and the Z order, I will get to it in just a bit. Now, with all this said, right, let's go step by step. The first thing is, the first problem that we need to solve for is how to get the data in. Now, the first problem that I would think a lot of people run into when you're dealing with multiple sources, writing to the same table, is basically the concurrency conflicts. If you're doing blind appends, you're not going to have a lot of problems because it's not going to conflict with anything else. Because a blind append is not going to, let's say, conflict with an update or something like that. But all other operations based on this table, they're going to conflict with one or another. The next one is the column size. Like I said, we don't necessarily have a lot of control on how people model their data. We can give suggestions, but at the end of the day, if they modeled it a particular way in their own system, they're not going to change it drastically by getting it over here. So what we notice in practice is once the column size hit 2 GB, where someone stuffed an extremely large piece of string into it, things start breaking down. And then the update frequency. This is not a problem specific to us. It's probably specific to everyone, because if you're going to have a lot of writes in a very short amount of time, you're going to generate a lot of small files. Now, every time that small file gets, as in you keep doing these updates, which are not appends, it's going to trigger a copy on write, which again is going to trigger a full rewrite of that file. Now, you might not see it from the execution standpoint, because all of that is abstracted to us from Delta, but there's a lot of pressure being put on the file system underneath, and it depends how well your provision worked. So the more updates, the more rewrites you need to do on HDFS. Thankfully, there are things like deletion vectors, etc., which takes a little bit of pressure off, as we're doing now. But those, I would say, are relatively newer and are being used. So talking about the writer conflicts themselves, right? We're going to focus on two things specifically to see how we mitigated it. Because the column size, obviously, we can put some guardrails around it, so it's not fun to talk about. One is, so let's start digging into the concurrency conflict first, and then we'll go a bit into the update frequency and how we solve that through the workflow. So what we ended up doing, Delta is based on an optimistic concurrency model. So two things conflict. One of them is going to win, the other one's going to roll back. In our case, when you have a huge amount of writes happening constantly, and given the marketing use cases, it's very expensive to do a rollback of something that's already there. It's probably better for you to just wait and then have the write run. Because one thing we did notice was a lot of the writes do happen very fast, whether they're inserts or they're updates. So what we ended up doing was we implemented a locking strategy on top of the DeltaLake table. So we partition the table out based on particular internal metadata that we know. Like, for example, one way to look at it is we partition based on source. Now, based on the source, we locked the source. So we basically put two levels of locks on it. One is a star level read-write lock. Star level meaning it's on the full table, this thing. The next one is a data set level lock, or like the source level lock. So what this ensures is even if there is a contention of write happening for a particular source, where let's say you're getting some writes from a streaming mode as well as a batch mode, we make sure that we obtain a lock, and whoever gets the lock, only they get to write. So before any writer can do anything, they have to first check, is there a star level lock? If not, is that a source level lock? And only then they can proceed. This has actually made a tremendous improvement in our overall latencies, as well as our COGS. The reason being, like I said, it's much more, first off, you're spending extra compute trying to contend for something. You lose because Delta says, no, you cannot write this, and then you roll it back, and you have to try it back again anyway. So you're wasting a lot of compute, which could have been used by somebody else at that same time. So this was one way, as in that we got it. And the locks themselves, they are maintained in Redis. So they're not local. So we have multiple clusters writing to it. So we're not limited to like within a single JVM or a single Spark cluster. This is orchestrated across a full region, across multiple different Spark clusters. And now, just to get over the full data flow as such, right? One thing that we did, like I did mention before, even when we were with the NoSQL DB, we did implement something called a CDC, or a change data capture. One change that we did was we did not depend on the change events being emitted by the database itself. A lot of NoSQL databases do allow you to publish their own internal binary formats out, so that you can take them, use Debezium or something like that, and replicate it somewhere else. What we did is we created something like an application level CDC. So only after a proper acknowledgement is received, post every write, do we emit a CDC message on the topic. Now, as I was saying, we already had a system in production serving a lot of customers, affecting a lot of revenue. on the NoSQL DB. So we couldn't just say, oh, we have this new shiny toy, we're just going to stop everything one day and do the other thing. So what we had to do was we had to do a gradual switchover of our workloads. So what we ended up doing was we took the NoSQL DB and we built like a backfill flow. The backfill flow was both partial backfills as well as full backfills, depending on which state of a migration the entire thing was on. And then the CDC topics, basically it was annotated with what tenant information that is there and what data is there. And it used to feed into a structured streaming application. And it went into something that probably has been there forever, ever since data warehousing has existed, something called a staging table. So we created a multi-tenant staging table, which is append only, which is extremely important because if you remember from the concurrency table, conflicts table, appends don't conflict with anything else. So this staging table is an append only log. Think of it as like whatever is there in Kafka. It's like a persisted Kafka using the DeltaLake. And the reason this works pretty well is because we have partitioned it by tenant and the fact that we have partitioned it along with time intervals. Because we are using this staging table as like a time buffered queue, and we have the time interval specified within it, we don't have any concerns about, oh, you're going to scan a large part of the table at any time. So this is basically acting as a work queue to hydrate what we say is something called a processor, which is again a multi-tenant non-structured streaming application, which basically checks for work every X minutes, and it's going to replicate it into the raw table, or in DeltaLake terms, we could call it a bronze table. Now I'm going to start with, so this problem specifically resolves the frequency of updates thing, because what we have created is the buffer. And this buffering helps us scale out, independent of how many, what kind of spikes come up over here. We could dig a lot more deeper into this, but the one thing that I want everyone to kind of see is on the raw table, the key thing is we have something called a JSON string. Up until the left-hand side, the data that was there, they were all individual fields, F1 to F1000 or whatever. But then what we ended up doing for this raw table that we are replicating to, we chose a complete anti-pattern, which was to use a JSON string representation. So I'm going to go a bit into that right after we just summarize the staging tables bit, right? Because the staging tables, what it ends up happening is the buffer helps us make sure that you're not going to read small chunks of data. Instead, you're going to optimize for larger chunks of data. And then the other thing is the multiple source writers issue that is also resolved. And from a logical view of the staging table, just so that to visualize it, the way to look at it is for every timestamp key that is there, like I said, we use 15-minute intervals. For every quarter that is there, you have a bunch of records in that bucket. So this visualization probably helps you think of it as like how we actually pick chunks of work. So every time the processor comes back up, it's kind of idempotent, right? It could probably, one set of transactions could take a lot of time, but you would basically pick all the pending work that is there. And you can also have guardrails set up over here, because each of these blocks, as they are conceptually and physically annotated by these timestamp keys, they have other metadata like how many records that are there, what is the size of the records that is there. So any type of planning you want to do in that processing layer, that can be incorporated using this as a base. And to track progress, again, one of the good things about Delta is you pick up a transaction, it's a 1 or a 0. It's not like 5 records are going to pass, the other 10 are going to fail. One of the main problems we had with the streaming store is sometimes what will happen, you might run into like some 429s or something like that. So you could have a batch of like 1 billion records. Probably half of them succeeded and half of them failed. Now, there's no way for you to know unless you're referring to an external source that something actually failed, and you have to go and correlate it. In the case of Delta, everything passed or everything failed. So now getting back to probably one of the burning questions some of you might have, why JSON string? This is not something that I see in a tutorial or a hello world application. Why are you doing something crazy like this, right? It did seem, this turned out to be, in a way, the more people we spoke to who were using Delta or adopting Delta around the 2021 framework, we were not alone. There were a few more folks who were actually ending up in this thing, and turns out it was for similar reasons, right? The first reason was, like I said, we had this nested hairy schema. Nested schema evolution was not supported in 2020. I know 2020 is like a Marvel Avengers time skip kind of a thing. It's like quite far back, but still it's quite fresh in our mind, right? So at that time, nested schema evolution was not supported. So we could not actually use it. But then Databricks actually delivered that like just 3 months after we complained, so which was great. But what ended up happening is, one of the things that I mentioned, we are not just a dumb append system or a put system. We also do UPSERTs. One example I can give you is a machine learning model generates churn scores. You already have churn scores. You want to probably update only for a subset of them. So they're not going to send a full billion row batch. They're probably going to send only just for the ones that have changed. And on top of it, because we support XDM as a JSON concept, the full JSON patch RFC applies to us from an ingestion thing. For those who you don't know, JSON patches are not good for your sleep. So we had to support this kind of evolution of the data itself for the data that we're managing. Now, how many of you have written UDFs? How many of you have written UDFs with dynamic types? Okay, great. So none of us could do that, right? Because every single tenant had a different schema. It was kind of impossible for us to maintain 10,000 copies of UDFs as schema is changing, for us to register it and put it in every single cluster. That would have been a fun project of its own if that is what we were getting paid for. But that was not the case. So it ended up being that, in a way, this approach that we took as a temporary approach till we got the fix from Databricks became much more easier, because the resolve and merge operations that we wanted to do, patch-wise and etc., are much more simpler on the JSON side, the JSON string side. You have tons of libraries which implement the JSON patch or RFC. Some do it better than the others, as we found out. But the thing is, doing those kind of operations on structs is not fun for anybody who's written with UDFs. So yeah. So the moment we actually did this and we were presenting it even internally, a lot of alarm bells went off. They were like, wait, you're going to lose predicate pushdown. It's like, what are you doing? As in, you're going to lose one of the main things that's coming out of this, right? So, but remember what I said. We were optimizing for the workloads that we had. And like I said, what we saw was the majority of the workloads were almost doing a full table scan anyway. But then came a very interesting comparison at the end of it, was that when we were reading this full JSON string and we were partially projecting it, it was still faster and cheaper than reading, let's say, a projection of fields from the existing NoSQL DB. And there are some very interesting reasons for that. I'm not going to go too much into this, but okay, I'll actually tell the reason why it's happening, because I don't want to wait all the way till the end of the thing. One of the things that we noticed was the compression ratio when we started storing things as JSON on string was through the roof. In some cases, things that were 100 terabytes on, like, say, the NoSQL database ended up being 200 GB on DeltaLake. So what we were doing was we were possibly hitting into the dictionary encoding or whatever things the compression does, and the amount of compression that we got was crazy enough to give us a better read performance, a raw throughput read performance through this approach, rather than actually trying to store them individually as structs and trying to evolve them and so on. Now getting into the table itself, right? The bronze table or the raw table that you're storing, we kind of had a very simple partition structure based on the query patterns that we had. The source ID is basically the source that it comes from. The timestamp is basically the timestamp of the event that comes with. But some interesting properties that are here that I want to share is mainly the table properties that we set, right? Forgetting everything else, there are two things I would draw your attention to. One is the data skipping num index columns. This actually made a pretty interesting thing. Like I said, we don't have 10 columns or 100 columns. We have thousands of columns. What Delta does, what it gives out of the box is basically stats building on top of all of these columns. In our use case, we actually wanted to disable it. So this option basically says only build the stats for the first 9 columns, ignore it for the rest. So this basically helped us avoid any unnecessary stats building that happens during the ingestion process. The next one is the deleted file retention duration. Anybody who's implementing GDPR, you should be aware of it, because whenever you do vacuum and all that stuff, you want to make sure that you're not holding on to data for a very long period of time. One question, at least internally, that got asked when we put this, key value data does not have event timestamps. What do you do? Nothing big. It just goes into a default high partition. So there was no necessity for us to split it into 2 different tables based on whether it was an event or a non-event. It just went into a high default partition. And here's the thing, right? The partition itself, it's not like you have one partition, it's a folder. You can configure what the file size is going to be, so you will get multiple different part files based on whatever configuration you set. So it's not like you're going to end up with just one single file which is like bloated up. Some more interesting things that we did, because we are coming from a NoSQL DB, the NoSQL DB itself has a concept of TTLs. Like you can say, hey, this record, or on Redis, right, for more people that are more familiar, you can say, hey, I want you to expire this document after 5 days or 5 minutes or whatever. Now, how do you implement something like that on the DeltaLake? There is no such concept of a TTL. So what we ended up doing was, I think it was simple enough, but I think it's cool at the same time, depending on who sees it. We basically defined a source level TTL. So every source has a config of what TTL is there. And we did 2 things. One is a soft TTL, and the other one is a hard TTL. The soft TTL is every reader goes through a reader SDK. So depending on whatever the dynamic config is, we basically rewrite the SQL query. So because it's a partition, whatever TTL we have set, it's at a partition level. It's actually very efficient in terms of doing the soft delete as well as the hard delete, because for the soft delete, it's nothing but a predicate pushdown with the partition filter, which is very, very efficient. And for the hard delete, again, it's still efficient because you're just dropping a full partition. Another thing which might or might not apply to a lot of you is, in our case, we are not managing a few Delta tables. We are managing same versions of the Delta table over thousands of tenants. Now, one way to manage it, well, initially there was no good way to manage it. But what we ended up doing was we implemented a pattern where every single mutation that happens on any DeltaLake table that we are managing gets appended to a central raw history table. So a lot of you might have built some tooling on the describe history of the Delta table. Now the same tooling, we applied it on one single extremely large table, which basically has the changes for every single table that we manage. This actually made our life quite easy, because when we're talking about thousands of tenants, doing Spark queries over or unioning the results over thousands of data frames is not exactly good. A few things about the performance, because we're running to the last 5 minutes. Cool things. I think all of you know Delta is already pretty efficient at doing a lot of things. But there were some things which actually surprised us quite a bit, because sometimes we take some things for granted. Like every CDC record that comes in, it's not equal with everything else. And what I mean by it is, one record might affect 10 rows, another record might affect just 1 row. One example of something affecting 10 rows is, let's say you get a GDPR delete. Hey, I raise a request to Nike, say, hey, I want everything for yesh@gmail.com to be wiped off, which means in terms of requests, it's a single request. But in terms of spanning, in terms of looking at it, how many partitions that spans, it could be quite an expensive query. So we wanted to see how much it takes. So what we basically saw was, in terms of as the row scaled, as the blast radius scaled, the delta writes also did scale appropriately. But there is one thing though, and this is where I want to call out the optimizeWrites. The same experiment, when we did it on OSS Delta, failed miserably. With the whole ingestion pipeline and everything, because the bottleneck was the ingestion. But when we turned it on or out on DBR, it actually did really, really well. The reason is the optimizeWrites, it makes sure that it's buffering before it actually ends up writing to the file system, and also making sure that you don't have too many small files there. So that helped quite a bit. This I kind of spoiled already, but key thing to note is the NoSQL store, one example we had, it had 1 TB of data on that. It translated to 64 GB when we actually moved it into DeltaLake. Other key points to note, the number of partitions. A NoSQL DB is a distributed DB, right? So the number of partitions that you have over there basically determines the throughput of your read or write for your Spark jobs or any other Flink jobs or whatever. But then note the number of partitions that you get on the DeltaLake side. So for us, we were heavily limited, one by cost and by the number of partitions on the NoSQL side. The moment we moved to the DeltaLake thing, our throughput basically shot through the roof. The same job that took 3 hours now took 25 minutes. And we were actually doing a lot more enhancements to see how we can get it down even more smaller. And these are full snapshot jobs. Now suddenly what was not possible before, which was incremental things, are now suddenly possible. So some cool stuff with respect to a numbers game. So we had 2 petabytes of data, which was not archived data, right? It's data that people are actively creating queries on, data that's actually making money, right? That was migrated in a live way as data was coming in. We right now manage, actually it's not 2K, it's 5K. We manage over 2 to 5K tables right now in production. We constantly run vacuuming and z-ordering on all of them. We have close to 20 to 30 billion messages per day in every region. So in terms of scale, this is a monotonically increasing thing, which is good. But it's also good because if we hadn't moved over to this, we would have keeled over and died. So some lessons burnt, important thing. Know your file system, right? Because of AWS, Azure, GCP, and all of them, no one's managing their own HDFS nowadays. If somebody is, I would love to buy you a beer, but yeah. This is so much taken for granted that a lot of the limits that we hit, we don't even understand until we have hit and an escalation has come up. So this is one of the things that we've had to iterate through and kind of fight with and negotiate with to make sure that DeltaLake as a tech works, but then it's not going to be magic unless you actually scale all the different parts of the stack along with it. And then another thing that we also invested in was multiple independent ways of statistical checking for the replication. It might not apply to a lot of use cases, but that's something that actually gave us a lot of confidence while we moved to a new system. So main takeaways, the scan IO from DataLake is way higher than the read from the hot store. You can get reasonably consistently, eventually consistent replication within minutes, not seconds. You don't want to do seconds. Then you'll end up with different problems like small files, etc. You do want to have a lot of data maintenance strategies like vacuuming, z-ordering, TTLs, etc. And I would use a staging table. Depending on if you have a streaming use case, do use a staging table. It'll save you a lot of pain and it'll help you sleep more. So that's about time. Hopefully this was useful. Thank you.
Thanks, Yash. So unfortunately, I think we're at time, but Yash, if you don't mind, maybe we can field some of the Q&A outside.
Sure.
Perfect, but thank you all.